Alright, today we're going to start binomial expansions, okay? Alright, here's really what you're going to learn today. You're going to learn the binomial theorem that's going to help you calculate binomial coefficients. If you don't really understand what that means, you'll understand it on the lesson here in just a minute. You're also going to learn about this little neat triangle known as the Pascals Triangle that can help you with this process. And you're going to use binomial coefficients to expand a binomial, which is really like the goal of this entire lesson. Okay? Now, I hope most of you remember what a binomial is, but if you don't and you're just kind of sitting there like, wait, what's a binomial? Just a refresher. Remember that a binomial is going to be a polynomial that has two terms. Right? Binomial. Okay, polynomial with two terms. So in this section, you're going to study a formula that provides a quick method of raising a binomial to a power. So, for example, let's pretend you have x plus y to the nth power, where n can be any integer. Okay. So, if you raise anything to the 0 power, it's always going to be 1, right? And if you were to raise it to the first power, well, it's always going to be itself. But if you do like square, that's the same thing as saying x plus y times x plus y, right? So what I'm going to show you today is how you can avoid taking a binomial and having to do, for example, if it was x plus y to the 6th power, x plus y times x plus y times x plus y times x plus y. Okay, so if you're able to use binomial expansion, you can avoid doing that many what's it called? It just went out, not foil. Just went out of my head. Oh my god. Distributions. Anyways. Alright. Okay, so first of all, we're just going to take a look at this and see if you observe anything. I actually wrote down some of the observations that I kind of wanted you to make on your own. But what I want you to notice is like the very first thing is that each expansion there are n plus 1 terms. So what I mean by that is take a look, for example, at x plus 1 to the first power. Well, the power is 1, but your answer has 2 terms. The power is 2, but you have 3 terms. The power is 6, but you're going to have 1, 2, 3, 4, 5, 6, 7 terms. Cool? The second observation that I would like you to make is that in each expansion, x and y have symmetric roles. What I mean by that is that the powers of x are decreasing by 1 successively, while the powers of y are increasing by 1 successively. Okay? So here's what I mean. Look at, for example, x plus y to the 5th power. Notice how you start with x to the 5th, and then x to the 4th square, x to the 1st. And lastly, technically you have an x to the 0, which you should know that it's 1. And now if you were to look at the y, you technically have a y to the 0 power here, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th. That's always going to occur. Okay? The very first variable is going to be decreasing in powers. The second variable is going to be increasing in powers until you match the power that whatever your binomial is being raised to. Okay? Number 3 is actually a little neat one where you can kind of check your work to make sure you're doing this right. The sum of the powers in each term is always going to equal to that power that you raised your binomial. So, for example, if you were raising x plus y to the 5th power, notice how on the expansion right here, well, all of your exponents, in this case you only have 1, add up to 5. On this one, 4 plus 1 is 5, 3 plus 2 is 5, 3 plus 2 is 5, 4 plus 1 is 5, and the last one is 5. Okay? Next observation I'd like you to make is that the coefficients increase and decrease in a symmetric pattern. So this is actually kind of neat, and this is why Pascal triangles work, and we'll talk about it here in just a second. But look at the leading coefficient, for example, on this one. It's going to be 1, and then the coefficient on this one is 6, 15, 20. So you go 1, 6, 15, 20, 15, 6, 1. So they're symmetric. 1, 5, 10, 10, 5, 1. 1, 4, 6, 4, 1. 1, 3, 3, 1. That pattern is always going to be there. So if you can recognize that pattern, you can save yourself a little bit of time while you're solving this. So for example, if you're able to find it, for example, you know that you're going to have 7 terms, and you find the first 4, then you can just know automatically what the last 3 are without having to really find them. Okay? All right. The coefficients of a binomial expansion are known as the binomial coefficients, okay? And I'm going to show you how to find them using the binomial theorem and using Pascal's triangle here in just a minute, okay? So, binomial theorem is as follows. If you're going to do the expansion of a binomial such as x plus y to the nth power, it's going to look something like this. Again, it's just an explanation of how the powers are decreasing for the first variable and increasing for the second variable. But I want to bring your attention to this. Do you guys recognize that notation? Combinations, okay? Combinations are going to be used here to help you figure out the coefficients of each of your terms, okay? So, now, if you don't recall how the combinations work, well, here it is, okay? You're going to have n number of terms, so you're going to choose however many you need, okay? And remember, combination is going to be n to the n factorial over n minus r factorial times r factorial. I want you to recognize that this symbol is the same thing as saying n choose r. Okay, so if you see either one of those, it's talking about a combination. Okay? Before we actually get to the binomial coefficients, we're just going to practice making sure that you can do this both by hand and in the calculator. So the very first one, if you were to use the formula, this is going to be 7 factorial over n minus r, which is 7 minus 3, which in this case would be 4 factorial times r factorial, which is going to be 3 factorial in your case. Now the neat little thing about this is that you can remember on section 1, we can rewrite this as 7 times 6 times 5 times 4 factorial over 4 factorial times 3 factorial, and then you can get rid of the 4 factorials. And then hopefully you can do this on your own, or if it's on the calculator then you can use the calculator. But 7 times 6 times 5, well, 6 times 5 is 30 times 7, it's going to be 210 over, well, 3 factorial is going to be 3 times 2 times 1, which is going to be 6. So 210 divided by 6 is going to be 35, I think. 35. Cool. So try the rest of this. Do them by hand, and I'll show you how to do it on the calculator. I think some of you guys probably already know, but if you don't, I'll share it with you here in just a second. Alright, check your answers. Make sure you got what I got. Any questions on how to do this by hand? This formula you would have to memorize if this is on the non-calculator part. Obviously, if it's on the calculator part, I'm going to show you how to do it on the calculator real quickly. So, on your calculator, if you hit the math button and you go over to probability, option number 3 gives you the option to do combinations. And the neat thing about this calculator is that it actually gives you a spot for you to type in your numbers. So 7 and 3, and you get the 35. If you are going to be using your own calculator and it looks like this, unfortunately for you, unless you have the update, I don't think it actually gives you the template. So if you were to just hit it, I'm sorry, I think it just does that. It doesn't actually give you a spot for you to put the numbers. So if you're going to use this calculator, you're going to have to input the number first. So for example, on this one, which is 7, so you got to first write the 7, then do the combination, and then write the 3. And you can do that as well. So like you can just do second enter again, and then change it to, for example, 10. Oh god. Did it not change? 10. Ah, yeah. Alright, whatever, 10. 3. But anyways, so there's both calculators, whichever you're using. That's how you go do it. Okay? Alright. Here. Alright, so now we're actually going to apply this into actually expanding a binomial. Okay? So we're going to start with something simple to the third power. Okay? So the very first thing you want to do is, if it's to the third power, how many terms are you expecting? 4 terms, right? Okay, so here's what I'm going to do. I'm going to leave a space blank for the coefficient that we're looking for, And then you're going to have the very first, which is going to be your very first variable, x to what power? Third power. And that's going to be multiplied by the second term here on your binomial, which in this case is 1 to what power? 0. Plus another coefficient times x to the second power times 1 to the first. Plus another coefficient times x to the first times 1 to the second. Plus another coefficient times x to the 0 power times 1 to the third power. So just to make sure, just check your work. You start at 3, 2, 1, 0, 0, 1, 2, 3. Cool? Alright. Now, to find our actual coefficient, so if we want to find that coefficient, how am I going to use the binomial theorem to find that coefficient? I got to do the combination of what? Okay? The very first term is going to be, well, n in your case is going to be your power. So 3, choose, and r is going to be the power of the second one, which in this case is 0. So for this one is going to be 3, choose 1. For that one, 3, choose 2. And for this one is going to be 3, choose 3. What I want you to notice is that this is going to remain constant. Okay? Your n, because that represents your power. Your r is going to represent this. Okay? So this is not changing according to the power of x. That's going to remain constant. Okay? Because that's the power that you started with. The only thing that's going to change is the second one, which is determined by the second variable. Cool? So then, one thing I wanted you to notice up here, and I forgot to mention, is that anytime you have a combination and your r is 0, you can avoid doing all the work because it's always going to be 1. So anytime you see something like this, it's going to be 1. It could be 4 choose 0, 100 choose 0, still going to be 1. And the other thing I want to bring to your attention is notice how when n and r are the same, it's always going to be 1 as well. So you can save some time there. So both of these are going to be 1. Okay? The very first term and the last term is going to be 1. Okay? So now, if you actually were to do this by hand, depending on whether it's on the calculator or non-calculator part, well, this one will be 3 factorial over, well, 3 minus 1 is 2 factorial times 1 factorial, right? Which is the same thing as that cancels out, leaving you with 3 over 1, right? Which is, this one will be 3 factorial over 1 factorial times 2 factorial, which is the same thing, right? Just rearrange. So this will be 3. Okay? So now, you found all your coefficients. All you got to do is now just clean it up a little bit. Okay? So the very first one, you don't really need to write a 1 in front, right? I hope you understand that. 1 to the 0 power is 1, so you just left with x to the third. Plus, well, 1 to the first power, 1 to any power is not really going to matter in this problem, right? So we're just going to have 3x squared. This one is going to be 3x. And the last one is going to be 1. Okay? Now, how could you check that you have the correct answer? You can use a calculator. So what I would suggest you do, if this is on the calculator part, I would go into the graphing function of your calculator, and I would actually plug in x plus 1 to the third power, and then in y2 I'd plug in what I found as my expansion, so x to the third plus 3x squared plus 3x plus 1. And rather than checking the graph, if you check the table, all the y values should be the same. So as you can see, for every x value, the y values will match for the entire. Okay, so that means that you've successfully expanded this without actually having to distribute 3 times in this one. Okay, so as you see, it's not terrible, it's just may take a little time. Cool. Alright, so here's what I'm going to do. I want you to try the next one on your own, but I want to bring your attention to the fact that this is minus. Okay, everything is going to work the exact same way. The only thing I'm going to tell you is, as you're working this problem, there's going to be a variation of signs. Your very first term is going to be positive, negative, positive, negative. Okay, so you're going to have this whole positive, negative, until you get to whatever many terms in this case you have. So in this one you're going to have 4 terms. I hope you see that. So it's going to be positive, negative, positive, negative. Cool? So try it out, see if you can get the answer, and then come back and check your answer. Alright, check your answer for the second one. I hope you realize that this was the exact same problem, so you didn't really need to do all the work other than just change the signs. Okay? So it's just x to the third minus 3x squared plus 3x minus 1. Okay? On the next one, everything is going to work the same way, but I want to bring your attention that this time you're going to have a coefficient in front of the x. But it's still the same. Since it's to the 4th power, you're expecting to have 5 terms. So you're going to have some coefficient times, well, your very first term of that binomial is 2x, so 2x to the 4th power. And then the second one is going to be 3 to the 0 power. Cool? And because it's minus, you're going to have that alternation of plus or minus, so you're going to expect, since this is positive, this is going to be minus, correct? And then you're going to have a coefficient there, and then you're going to have 2x to the 3rd power times 3 to the 1st, plus some coefficient 2x to the 2nd power times 3 to the 2nd, minus some coefficient 2x to the 1st power times 3 to the 3rd, and then finally plus some coefficient, and I'm running out of space, times 2x to the 0 power times 3 to the 4th. And again, you have that pattern of 4, 3, 2, 1, 0, 0, 1, 2, 3, 4. Cool? Alright, so now all you're going to do is use combinations to help you figure out each one of this. Well, this one is going to be 4, choose 0. For that one, you're going to do 4, choose 1. For this one, you're going to do 4, choose 2. 4, choose 3. And 4, choose 4. Right away, you should be able to tell that this is 1 and this is 1. And if you actually work those out, I'm just going to do them on the calculator now. So, 4, choose 1. 4, math, probability, choose 1, it's 4. Then 4, choose 2 is 6. And then 4, right? Now, did I really need to type in to find that was 4? No, I could use that pattern of symmetry. So it's 1, 4, 6, 4, 1. Cool? It meets that criteria. Now, you got to clean this up a little bit, okay? Alright, this 1 is really not going to make a difference. This 3 to the 0 power is not going to make a difference, but 2x to the 4th power becomes what? 16x to the 4th power. Cool? Then you're going to have a minus. Alright, so this 3 to the 1st power is going to stay as 3. 2x to the 3rd power, or, well, 2 to the 3rd power is 8. So 8 times 3 is 24, and 24 times 4 is 96. X to the 3rd power. Cool? And then the next one, so it's going to be plus, and things might start to get a little bit tougher if you need to write them down. It's up to you. But 2x to the square is 4x squared. 3 squared is 9. 9 times 4 is 36, and 36 times 6 216. Yep. Again, you can, if you need to take steps to do that, that's fine. I just ran out of space. So it's 216x squared. Cool? Minus 3 to the 3rd power, well, 3 to the 2nd is 9. 9 times 3 is 27. 27 times 2. Okay, 54 times 4. 216 again. So 216 x, and lastly you have plus 3 to the 4th, 81 times 1, 81, right? Okay, and this is your expansion for that expression. here's what I want to bring your attention to. You have that symmetric pattern with the coefficients prior to doing the simplification of it. That doesn't mean that this is going to happen here, okay? So don't just do this 3 and then expect that to be 96 and this to be 16, okay? The symmetric pattern happened with the coefficients itself that we found. Cool? Questions on this one? Alright, I hope you realize that it's not terrible, okay? So now what I'm going to do is I'm actually going to show you an alternate method of solving this, okay? Which is using something called the Pascals Triangle. Now some of you guys have probably seen this or heard of it. Some of you guys know how it works. Some of you guys just seen it but don't really know how it works. But by arranging numbers in a triangular pattern, you obtain the following array, which is called Pascal's Triangle. This triangle is named after famous French mathematician Blaise Pascal. Okay. So here's what he did. Notice how the first and last number of each row is 1. You guys notice, like, okay? Now, if you notice in your expansions earlier on the page, wasn't that the case as well for all of this? Right? Okay. It says, every other number in each row is formed by the sum of the two numbers immediately above it. So the way that this works is, for example, if the very first one is 1, couldn't there technically be a 0 here? Do you guys agree? Technically? And what's 0 plus 1? 1. Technically you can have a 0 here, right? 0 plus 1? 1. You could have a 0 here, 0 plus 1, 1. So do you see how I'm going to continue to get 1s along there. But for everything on the inside, check this out. For me to get that 2, if I do 1 plus 1, that's 2. 1 plus 2, that's 3. 2 plus 1, that's 3. 1 plus 3, that's 4. 3 plus 3, 6. And that's how you can create and keep going as many times as you need it. Okay? Alright. One thing that you need to know about it is that this is known, Pascal has rows. Okay? But unfortunately, I don't know why they chose to do it this way, but well, actually, I see why they chose to do it this way, because it helps you, especially with binomial. This very first term is known as the 0th row. And then this is your first. This one right here. And so on. Okay? So the very first one doesn't happen to be the first row. It's the 0th row. And then first, second, third, etc., etc. Okay? Now, does anyone notice anything particular about Pascal's triangle? Tie it to a sequence. We've already kind of had this sequence come up on like the very first day, I think. Don't look at each individual number, look at each row.
Is it n squared?
11 to the power. So 11 to the power of 0 would be 1, right? 11 to the power of 1 would be 11, right? 11 to the power of 3 would be 121, right? 11 to the power of 3 would be that. But we're going to run into a problem because eventually when you exactly, hold on. So there is a way that they actually worked around this, okay? Let's talk about it. So look, if you do 11 raised to the x, let me go to the table. So you see how that's the 0th row, 1. And this row is 1, 1, right? So that's the 11, right? The third row is 1, 2, 1, which is the 121, right? So you guys see how that's happening? But then when you get to, I believe, 4, is that still matching? 1, 4, 6, 4, that's still matching. And then you get here, and then we have a problem. Do you guys see that? It's no longer the same, okay? The way they kind of did this, and let me see if I can explain it. I'm going to go on the board. So I'm going to pause the video just a second. Alright, so look at, I'm sure that you can use the Pascal's triangle on your own, so I don't really have a problem for you to practice on that. You can apply it to the problems that we did. But I want to bring your attention to the way that some of the book asks some questions in this manner, and I want to make sure that you understand what it's asking. So it says, use the 5th row of Pascal's triangle to find the binomial coefficients. So if you're using the fifth row, okay, it says, this is the way the question is going to be worded. It's sometimes misleading. You have to use the fifth row to get the sixth row. Okay, so we're going to be using the fifth row to get the sixth row, which would be the numbers that are on these combinations. Because if you think about it, again, just to what I was explaining earlier, if you're using the fifth row, that's going to help you find the coefficients of what? What expansion? To what power? To the fifth power, right? But how many places are there on the fifth power? 6. Okay? So when 0, correct? And then 6 choose 1, 6 choose, etc. That's it. I know it's kind of, I don't like the way it's worded on the book. I just wanted to explain it to you. Okay? So I'm sure you can handle it this. Okay? So if you were to do 6 choose 0, you get what? 1, right? Okay? And then if you were to do 6 choose 1, you get 6, and so on and so forth. So you can do 6 choose 2, I don't know what you get. 15, and then 6 choose 3, 20. So there's 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, and I hope you can recognize that after that it's going to follow that pattern, right? Cool. Alright, so you can try the next one on your own. It's going to say use the seventh row to find of Pascal's triangles to find the binomial coefficients. Alright, so I constructed here a Pascal's triangle to help me answer the question, which if you were to input that in the calculator, you're going to get those numbers there. Cool. Alright, next one, it says finding a term in the binomial expansion. Alright, so if you have an expansion of x plus y to the nth power, r by n, choose r, where x is n minus r and y is r. Okay? Do we all understand what that means? Are we a little confused what that means? What this is saying? Does anyone need clarification on what that means? We don't understand what it means? Okay. So, rather than me asking you for for the entire row, so like for all these numbers, I could be very specific and ask you, what would this term be? Like, what would the coefficient of this term be? And if you do the triangle, then you would do 56, right? But you wouldn't want to have to do all this, right? You might just want to, like, if I'm just asking you for one specific coefficient, you want to just find that coefficient. You're welcome to do all this, but if there's a way that you can avoid doing all that process just to find the one term that I'm asking you for, then this is what this is for. Okay? So let me explain to you what this means. So for example, I can ask you, find the sixth term of this binomial here to the 8th power. So the way it's going to work is, do you agree that this is the way we've been doing this? That's the coefficient that we're looking for, right? Okay? Now it says, you're going to take, in this case, x for you represents what in this problem? A. And it says to do what? N minus r. Well, what is r? What do we mean by that? Well, look at this. It says the r plus 1 term. So what's the term that we're looking for? So wouldn't this be r plus 1 equals 6, right? So that means r in your case is 5. You see that? So that means that this is going to be n minus 5. So in this case, you have 8 minus 5, which is 3. And then you're going to have 2b to what power? Well, it says just to r, correct? So your r is 5. Cool? Now, how can you make sure that you're correct on this? Well, what's 5 plus 3? And remember how the powers need to add up to be the whatever you're raising your binomial to? Now, if you're really doubting yourself and you want to do this, you could do this, honestly. You could say, well, the first one's going to be a to the 8th, b, 2b to the 0, right? And the second one's going to be a to the 7, 2b to the 1st. And you can actually list them out if you want to. It's up to you, honestly, so you can figure out what it is. But that's what we're looking for, okay? So now, the 3, okay. The 3 is going to be, once you figure out what your R is, okay, you're going to subtract it from the highest power. Your N represents, in this case, 8. So once we figure out what R was, we did 8 minus 5. That's how we got the 3, okay? All right. Now my question to you is, what combination do I have to use to find out what that is there? So N is going to be what in this case? 8. Choose, well, you found your R, didn't you? Your R was 5, so it's always N choose R, right? So in your case, it's going to be 8 choose 5, okay? So then if you use your calculator or you use the formula depending on what it is, we're just going to use the calculator for time's sake. 8 choose 5. I get that number, 56. Cool? Alright. So 56, but is that going to be your answer? No. You're going to have to simplify what you have here. Okay? Well, the a to the third is not going to make a difference. Do you guys agree? You're still going to have a to the third. But 2b to the fifth power is going to make a difference. So 2 to the fifth power is 32, right? So this becomes a to the third times 32b to the fifth times, in this case, which is 56, correct? So when we simplify that, 56 times 32, it gives me 1,792, a to the third, b to the fifth. So the coefficient that we were looking for is 1,792. Yeah, that's fine. I'll accept it. That's fine. So like part B is the same thing, but it's just questioned a little different. I'm actually giving you how it looks. Okay, I'm asking you to find the coefficients on it. So try it out. Try it on your own, and I'll show you the answer here in just a second. Alright, so here's the answer for part B. For homework tonight, page 604. Next time we'll review